Today's problem was submitted by a viewer, and it says, the parabola y is equal to x squared rolls around the fixed parabola y is equal to negative x squared. Find the locus of its focus, which is initially at the point x equals 0, y equals 1/4. So this is a Putnam question. The viewer has said this comes from the Putnam contest in 1974. This is question A5. I attempted the Putnam once when I was a university student. I honestly do not remember at all how well I did. It probably was not that well, and I don't remember any of the questions from it at all. So let's first try and understand exactly what this question is asking. So we have two parabolas, the standard y equals x squared parabola. And we have its reflection. Can I can rotate it like this. Okay, so we have two parabolas like that. A parabola has something called a focus, but if you imagine the parabola as a mirror and straight lines of light come down like this and reflect off of it, parabolas have a feature that all of the reflected rays will meet at a single point. That point is called the focus. Now it's given to us. I could derive where that focus is using some standard methods, but we're told that the focus is at the point 0, 1/4. Now the question also says the top parabola rotates around this other fixed parabola. So if you think of the top parabola as being like a wheel, a really strange shaped wheel, then maybe I can do it like this again, highlight that. The points are going to stay in contact, and the top one is going to rotate around the bottom one. So as it moves, rotates like that a little bit and kind of spins, and always will stay in contact like so. And of course, as it does that rotation, the locus, or the focus, is also going to move, and we're asked to find the locus of its focus. So we want to find the curve that this point moves through. I believe that is what we're being asked to do. Okay. So I think what is the best way to do this? Like, I want to parameterize things in some way. Like maybe I should parameterize everything by the x coordinate of the point of contact, because in some way I suppose, as long as these things aren't slipping, if I take 2 points on each parabola that correspond to each other like this, then as the top parabola rotates, the points that will come in contact, like the point that they will share in contact here, it is going to be that point. So as it rotates, pairs of points will meet up together like that. This is the point on the top parabola which will touch that point on the bottom, and so on. This is the point on the top parabola which will touch that point, and so on. So I think the state of the system, if I think of this as like a dynamical system, it can be parameterized by the x-coordinate of the point of contact. And then so in fact, I'll call this t, right? T is our parameter. Think of it as like a time parameter. Which is the x-coordinate of the point of contact of the two parabolas. Okay. So what I want to do now is I want to sketch the diagram. I want to sketch the diagram in an arbitrary state for an arbitrary value of t. And one thing this might allow me to do, there's a few things that I might be able to do then, is compute the angle that the top parabola has rotated through. You know what's interesting here? Okay. So the fact that the x-coordinates are the same of the corresponding parabolas of the meeting point is that well, it's not to say that this point, does each point in this parabola then only move up and down? No, absolutely not, right? This point, when this point is touching there, this point is going to be way over here. There's one value, there's one point on the locus of this that would be easy to find. If we take a slice here, find that point, drop that down, the focus is going to be over here somewhere. Right, this shape. That'll, like, I guess this is an x value of 1 over 2. So the focus will pass, this point here is at 1 comma negative 1 over 4. So when I do it in generality, we should check that this point as a sanity check. We should verify that that point is on the locus. And similarly, if we rotate the other direction, also negative 1 and negative 1 over 4. So that'll just be like a sanity check to make sure that whatever formula we derive satisfies that those 2 points are on it. Yeah, I'm just trying to think now about what the best approach is here. Do I want to compute the... I probably will have to compute the angle that it's rotated through. And when I say angle, I'm going to say, I'm going to classify that as like, if I draw a tangent at the vertex of the parabola, essentially what is the slope of that tangent? Okay, let's get started. I'm going to copy this diagram and go through the computations with like a fresh thing, but I don't want to erase that in case I need to come back to it or something like that. Okay, so I'm going to No, I don't want to erase that. I want to rotate it. Let's rotate it some amount. This is over here now, something like that. I feel like I need to make the whole diagram, I need to zoom in. Okay. I'm going to draw a new diagram and sort of exaggerate some of the features of things. So this parabola y equals x squared. Something like that. So let's call this point here, that's t on the x-axis. So then this here is negative t squared. If I draw a tangent line there, the slope of this tangent line is negative 2t. Okay. And so its angle, and I'm using the standard convention of angle with respect to the horizontal axis. How does this work? Is it arctan, tan inverse of negative 2t? Make sure I didn't screw that up. So if I have a line with that slope, theta, tan theta is this. Yeah, okay, that's fine. So that's the angle that this line makes with the horizontal. If I do that, it's the angle there, okay? So the angle of the original point on top parabola is arctan inverse of 2t. So when this point is going to touch that point, that slope is negative 2t, and the slope at the corresponding point up here is 2t. So when this comes down to there, I mean, we have obviously it rotates through double the angle, double that angle. So that's the rotation. the rotation angle is the final angle minus the initial angle. Okay. Because now what I can do, if I take an arbitrary value of t, like this, and I compute the location of the focus relative to this point has moved here. But this vector, it doesn't rotate, but, I mean, the, how do I want to say this? The origin point of this vector, I know where it goes to, and the direction of the vector just rotates. So let's call this v of t, like that. And what we're told, so v of t is equal to t comma t squared minus 0 comma 1 over 4. If I rotate, I'm going to call this angle theta. That's the angle that we rotate. So what I want to do then, the new location of the focus is going to be at this point plus the rotated vector v. So I'll call this the position of the focus is going to be at t comma negative t squared plus the rotation, I guess I should call this theta t, the rotation theta t applied to the vector vt. So we rotate by an angle of theta. What is that matrix again? Well, 1, 0. Rotate by theta, this goes to cosine theta, sine theta, and r theta 0, 1 goes to negative sine theta, cos theta. Okay, so r theta is cosine theta, negative sine theta, sine theta, negative, positive cos theta. Okay. So I can write the answer. The focus is located at t comma negative t squared plus this matrix applied to the vector, what is it again? T squared minus the original focus. Let me write this as a column vector. Okay, where theta t is tan inverse negative 2t minus tan inverse 2t, which in fact that's equal to, tan inverse is an odd function. So that's negative tan inverse 2t. The by the way, hold on a second. Hold on a second. I need to think about that again. Can this ever rotate by 90 degrees? This might be wrong. That might be wrong. In fact, it probably is. Let me get rid of this. Because, so remember I took that by saying this point dropped down. I assumed that it was going to rotate 180 degrees, but I don't think that's possible. Maybe it is? Hold on. Oh man. I'm going to continue with this algebra, then I'll come back and think about the intuition of the geometry. Minus tan inverse 2t. So this is negative 2 tan inverse of 2t. So I wonder if cosine theta and sine theta can be simplified from that. Yes, like, okay, so let's, obviously the slope anywhere along the parabola, it never reaches negative infinity. So the angle of rotation did I I suppose like asymptotically the rotation approaches the total rotation approaches 180 degrees. Okay, now it makes sense. Yes. As t goes to infinity, this goes to 90 degrees. So the rotation approaches negative 180. That makes sense. The parabola never quite fully turns upside down. So that thing I had written up here, that was totally wrong. Totally wrong. If anything, when the horizontal point comes down here, like that, it'll have rotated 90 degrees. So the correct value, the correct certain, like known value of that locus, it'll be, will it be on the axis here? Right, this value here is t over 2. is equal to 1 over 2, then I really did not draw this to scale at all. Let's get another color going on here. Oh, sorry, not t over 2, 1 over 2. This will be 1 over 4. Negative 1 over 4. This, when t is equal to 1 over 2, the slope of this line is 1. So the slope here is negative 1. So it's rotated through 90 degrees. So the focus will be at so this point ends up here. The vector v is that one, and it gets rotated 90 degrees, negative 90 degrees. So it'll be at this point pointing straight up. So one point that's on the focus certainly is 1 over 2 comma negative 1 over 4 plus this vector pointing straight up. This vector is of a length of a half. So I think this point should be on the locus, and that corresponds to t equal a half. So I'm going to substitute. I'm going to take my formula here. Before I continue and try and simplify everything, I'm just going to take the formula and plug in t equal to a half and make sure that we're on the right track. So pt is 1 over 2, negative 1 over 4. Well, let's compute plus r of theta 1 over 2 applied to v of 1 over 2. Theta of 1 over 2 is equal to negative 2 arctan inverse of 1. Arctan inverse of 1 is pi over 4, so this is negative pi over 2. Okay. So then r of theta is cosine negative pi over 2, negative sine negative pi over 2, sine of negative pi over 2, and cosine of negative pi over 2, which is cosine of negative pi over 2 is, oh no, pi over 2 is 90 degrees. So that's 0, 1, negative 1, 0. Okay. And I need to take, so when t is equal to a half, this is just equal to 1, 0, right? Applied to 1, 0 is equal to 0, negative 1. Have I done something wrong? Oh, yes, I have. I've done something wrong. in computing this vector, it's this point minus that point. So I've got this expression for VT is backwards. It's like that. Okay. Should be 0 minus t 1 over 4 minus t squared. Okay. So when t is equal to a half, well, I'm not, yeah, I don't want to apply it to this vector. Hold on. The rotated vector I had that wrong earlier anyway. Okay. When t is equal to a half, I have negative a half, 0. So I need to take the first column, multiply by negative a half, so this equals 0, 1 over 2. And so PT is equal to this point plus that thing I just had. Yeah, it's 1 over 2, negative 1 over 4, plus 0, 1 over 2, which is 1 over 2, 1 over 4. Okay, I'm confident at this point now that my general expression is correct. That's the locus of points of the focus, parametrized by the x-coordinate of the contact point of the two parabolas. I'm sure this can be simplified a whole bunch by using some trig identities, right? You know, if we take this and substitute it in there, you might have some double angle formulas for things. There might be a double angle formula for arctan, I don't know. Let me write out in full what I have here. Let theta t be equal to negative 2, arctan of 2t, r theta t is a rotation matrix, cosine theta t, negative sine theta t, sine theta t, cosine theta t. Locus of focus is PT is equal to, what did I say? T negative t squared plus r of theta t, the matrix, multiplied by the vector negative t 1 over 4 minus t squared. Make sure that's what I had written. VT is negative t and a quarter minus t squared. Yeah. So again, maybe there is some simplification you can do of this rotation matrix. You can probably write it. You can probably, with that, with some trig identities, double angle formulas, you can probably write these as like rational functions of t. Like, I don't know, t over 1 plus t squared, or root of 1 plus t squared. Not quite rational functions. There might be some square roots in there. But I'm sure that's just like a some trig identities, some double angle formula stuff. I don't know. I don't think that's a terribly important part of this problem. The main thing to understand in this problem that allowed me to get anywhere is understanding that as the top parabola rotates, let me erase some of this. As the top parabola rotates, the 2 points on each parabola that contact each other are going to be points that are directly vertically on top of each other before any motion happens. And I mean, because the parabolas are exactly the same, just flipped, you know, the length, if you trace the point of contact, right? If you trace the point of contact, then obviously on one parabola, it's just going to trace downwards like that. Well, the length of that curve has to be the same as the length of the point of contact on the other parabola. And so that's where you get that from. If the other parabola, if the two parabolas were something like y is equal to x squared and y is equal to negative 2x squared, this problem would be a lot more difficult, because then it won't be points that are directly on top of each other. You know, you'd have like, you know, this point here might correspond to that point there. You would have to take the length of this curve and find the curve on the bottom parabola, which is the same length as that one. And that might end up having different x coordinates. This would be like super complicated. This is a cool problem. Again, like the viewer in the message they sent me said that there's several ways to solve this fun problem. I'm not sure what other ways you could use to do this. It was arbitrary the way I chose this free parameter of the problem, but maybe you can do things differently where you choose the angle theta to be your parameter, but then you have to solve for the point of intersection as a function of theta. I feel like that would be very similar. You would just end up having a lot of inverse formulas for things. Yeah, but no, I thought it was a cool problem. Again, I'm not concerned. I consider my answer, if it is correct technically, you know, I consider it complete enough to call it correct. Again, I'm certain there's a lot of simplification that can be done here, but that would just be a question of looking up trig identities, which I don't think is really terribly important for the nature of this problem. Anyway, thanks for the submission. If I have any more to say about this one, if new thoughts come in, or if in the meantime I find I've made a mistake, then I'll post something either in the description or on the video itself. Thanks for watching. So I'm returning to this problem after a very short time because I had a brief correspondence with the person who sent this in, and they alluded to something that tells me the solution can be simplified a lot, and the answer is actually something that I didn't expect. So what I'm going to do here is I am going to simplify this rotation matrix, every term in here, using some standard trig identities, and then compute everything in this expression here to see what we end up getting. So the trig identities that are going to be important are some pretty standard double angle formulas, except rewritten in terms of the tangent of the original angle. So that's a double angle for cosine, and a double angle for sine is given by this. And so I'm just going to substitute this quantity in for cosine 2x and sine 2x. And because x itself is written as an inverse tangent, all the appearances of tan or tan squared x will just turn into 2t. So I'll go through these computations, and then we'll see what the final result actually looks like. So there are the two trig ratios which appear all over the rotation matrix, so we can compute the full rotation matrix now. Okay, and this rotation matrix has to be applied to this vector. So let's go ahead and work that out. Okay, and there's the result of multiplying the rotation matrix by the vector v. Somewhat surprisingly, we get a 0 in the first coordinate. And finally, we need to take this expression and substitute that up in here. So that's the thing that I've just computed, so I need to add this quantity to it. So I have 0, 1 over 4 times 1 plus 4t squared, and I have to add t and negative t squared. Oh, I have a mistake. I canceled something in the wrong way. Yeah, it's 1 over 4 times 1 plus 4 t squared, like that. And so the result here, so we get t in the first coordinate and 1 over 4 in the second coordinate, which is a parametrization of a horizontal line through the original focus of that parabola. So if I plot what's going on here, there's the original parabola and the rotated version. And here's the focus of the first parabola. So as this top parabola starts to roll downwards along that parabola, the focus actually just moves perfectly horizontally. It was pretty counterintuitive to me once I saw how all this algebra ends up working out. Of course, if you can extend it to rolling to the left as well, so you just get the locus is this horizontal line at a height of 1 over 4. In my head, the point was moving downwards somehow, but it just so happens that's not how the result works out. So I'm happy I had that very brief conversation with the person submitting it, because they just said something about a straight line, and instantly I knew I should definitely go back and simplify some of the expressions I had, and it works out pretty straightforward that we get a horizontal straight line going through the original point. So thanks again for the submission. shows that if you remember simple things like trig identities, you end up with a big simplification. It corrected my intuition for what was going on. Yeah, don't really have much more to say about this one. Thanks for watching.